So again, this is our last topic in Unit 3, coefficient of variation. So first question is, what is it? And the coefficient of variation is a measure of spread that describes the amount of variability relative to the mean. It's similar to the standard deviation. Because the coefficient of variation is unitless, you can use it instead of the standard deviation to compare the spread of data sets that have different units or different means. And here's your formula for this coefficient of variation. It's the ratio of the standard deviation. Remember, S stands for standard deviation. In fact, it's sample standard deviation of a sample. And then this underneath in the denominator is X bar, which means sample mean. So standard deviation is in some unit of measure. Mean would be in that same unit of measure. And when you divide one by the other, they cancel out, so that's how you become unitless. We could also write this formula using our symbols for population mean. Sorry, sigma goes on top. Population, standard deviation, divided by population mean times 100. Why do we multiply by 100? Yes, to get a percent, because that's what it says right here, expressed as a percent. So we have an example. Isaiah, will you read the example, please?
You're the quality control inspector at a milk bottling plant that bottles small and large containers of milk. You take a sample of each product and observe that the mean volume of the small containers is 1 cup with a standard deviation of 0.08 cups. And the mean volume of the large containers is 1 gallon, or 16 cups, with a standard deviation of 0.4 cups. Although the standard deviation of the gallon container is 5 times greater than the standard deviation of the small container, their coefficients of variation support a different conclusion.
Very good.
What does any of that mean?
Good question. It's a lot. So what this conclusion is saying is, hey, here's this larger milk container, right, the large one. The mean for the large milk container is 16, right? So if I were doing my normal distribution for that, I would put 16 in the middle, and then the standard deviation is 0.4, so I would be going up by 0.4 each time. So 16.4, 16.8, and 17.2, and down 0.4 each time, so 15.6, 15.2, 14.8. Remember this? Right? This is where we calculated, hey, 1 standard deviation from the mean is what percent of the data? 68. And 2 standard deviations away is what? 95. And then 3 standard deviations away is 99.7. So this spread is 4/10 of a cup when we have 16 in the middle. And that was for our large containers. Versus our smaller containers, we could make a normal curve and put the mean in the middle there of 1 cup, and then 0.08, so it'd be 1.08 and 1.02, and we could create the normal curve with respect to 3 standard deviations from the mean there. What this is all saying is a standard deviation of 0.08 compared to 0.4 is much smaller. That's a smaller spread, just looking at those two numbers. But when we take into account the mean of those data sets, 0.4 doesn't seem so large when we're thinking about 16 in the middle. And 0.08 seems a little bigger when we're only talking about 1 cup. So to account for that relationship to the mean, we do this calculation here. So they did the times 100 at the beginning, so you can kind of keep that in perspective. They just shifted it over, and that's legal. So here is the 0.4 cups, so there's your standard deviation, divided by your mean. So they just applied this formula, standard deviation by mean. And for the large container, the coefficient of variation is 2.5. Versus the smaller container, where they divided the 0.08 by the 1 and got a coefficient of variation of 8. So when you actually relate things back to the mean, that really allows us to compare the two data sets in a more accurate way. So at that point, the small container really has more spread than the large container. Questions? Yes?
Should the 22 to the left of 1, or the 22 to the left of 1 be 0.02, or you read it as 1?
Yeah, thanks. Quick fix. Good job. All right, flip over that paper. And we just have a few practice questions to work through that formula. So write it on the back. It's kind of nice to have it on the back so you don't have to keep flipping back and forth. So here's the question. Which one goes on top? Which one goes on the bottom? Yes, good job. I don't know why I mix those up sometimes. So here is your formula that you will be applying to these questions. So we have a set of data that has a mean. So here's my x bar and a standard deviation of 11. Even though I know this formula, I still sometimes try and divide the wrong number. I don't know why that happens. So make sure you have the right number on top. So CV equals 11 divided by 88 times 100. You'll need a calculator at this point if you don't have one already. What'd you get, Bree? What'd you get?
12.5.
12.5. Anybody else? Agree? Yep. All right, yeah, thanks. 12.5%. So the coefficient of variation is 12.5%. That doesn't even look like a 5. 12.5% for number 1. For number 2, again, we have the mean and we have the standard deviation. So CV equals 12 divided by 1200, S divided by x bar times 100. And raise your hand when you're back. What do you get? 1. 1%. Yes, agree? Great. It's probably getting the hang of this. We'll skip 3 and look at number 4 because things change up a little bit. Number 4, you can see they've given us the mean, x bar, but they've given us the variance. Does anyone know the letter that we used for variance? Do you remember? S squared. Right. So if S squared is my variance, we can easily calculate the standard deviation, S, by simply taking the square root. And now I have everything I need to plug in to my coefficient of variation formula here. So I do CV equals 6 divided by 118. What did you get for that one, Tyler?
I got
5.01. Anybody agree?
5.01.
5.08? Oh, so if you, would you round it to 5.1? Oh, okay. So you could say 5.1% if you round it, or 5.08% if you kept one more decimal place. Either one would be acceptable. So I want you to try questions 3, 5, and 6 on your own.